Welcome. Welcome. I guess we're live. Can everyone hear me?
Yeah.
Yes.
Okay, perfect. Hello, everyone, and welcome to our first roundtable on understanding Ouroboros, Leios. We're thrilled to have you join today's session. My name is Denisio Butte, and I'm co-hosting this session with Rick McCracken. Rick, it's great to have you co-hosting this session. Exciting, man.
Oh, you're muted, Rick.
All right, thanks for having me on, Denisio, and welcome everyone else. I'm really looking forward to learning more about Ouroboros Leios. I've watched the videos that were put out by IOHK with Agalos, and I'm very happy that you guys are doing this. I would also like to say, Denisio, I'm very glad to see you doing this kind of platform for the Cardano community. I love this kind of stuff, and I'm looking forward to you doing more events like this in the future. So thanks a lot for getting on this. I very much appreciate it.
Yes, Rick, and yes, indeed, there will be much more. So this roundtable series is designed to provide the community with educational content that breaks down complex topics into easily digestible insights. And by doing so, to we hope to support our builders by fostering trust and community engagement with our ecosystem through education. So today we're honored to have two distinguished guests with us, Pi Lanningham and Arnaud Bailey. Both Pi and Arnaud are renowned for their in-depth understanding of Ouroboros Leios, and we're excited to learn from their perspectives. The session is part of our ongoing effort to enhance community knowledge and support the growth of our ecosystem. We'll be discussing key topics related to Laos, helping demystify the complex subject for everyone. Our roundtable format, as Rick just mentioned, will be topic driven and featuring rotating hosts, ensuring that we have a diverse range of not insights but also discussions. And the session we're hoping to reach users on X and also on the reactivated YouTube Cardano community channel. So if you haven't subscribed, please do so now. Just like our content, other content from the ecosystem that we try to amplify, this format will also be published on the Cardano.org news section so that it can be accessible to everyone in the long term and independent of platform. Before we get into that, at the end of this presentation and the discussion, we'll open up the floor for a Q&A session. But before we get to that point, Rick, how's it going?
Yeah, it's going really good. I just left a Twitter space. It's still ongoing. We were doing the governance. We were having the different participants in the interim constitutional committee giving a quick rundown of what we were doing there. So that was fantastic. Really loving that. Very happy with how everything's going in Cardano with moving forward with governance in the engineering side here with Ouroboros Leios and what we're going to expect to see, how Ouroboros Leios works, how does it improve the Cardano network performance, all that kind of cool stuff. So thank you.
Nice. So thank you, Rick. Without further ado, let's turn to our guests. Pi, Arnaud, thank you for joining us. Could you start by just giving us a brief overview of your background and what excites you most about Ouroboros Leios?
Yeah, hi. Thanks for having us on, and really excited to kind of be the first guest or among the first guests on this roundtable format. My name is Pi. That's like the number. Was very pleased that I could put the symbol in Streamlabs, so that's pretty cool. I am the CTO at Sunday Labs. We built the first AMM-based DEX, and we are kind of just a software consulting company trying to, in general, promote Cardano in any ways that we can. I am really excited about Leios, and in particular, wrote a pretty popular Twitter thread about it, and really just kind of want to help people understand, that fundamental intuition of how does it work and what benefits does it provide, and then also we'll have some conversation with Arnaud about what trade-offs it makes to get there, because engineering is always about trade-offs.
I'm Arnaud. I have been working on Cardano for various projects. I'm currently working at IOG as an architect, and I am part of the what we call the R&D or innovation streams project, and currently focusing on two extensions or two new protocols. So Peras and Leios, so we are just starting this. So Leios paper was published, or I don't know, 2 weeks ago, 3 weeks ago. So we are really only started right now setting up the stage and setting up the team to do the work, the needed work to turn something which is a very cool idea with solid theoretical background and into something that can actually be implemented on Cardano. So that's my job, and my goal and my role here is really to convey the idea that how exciting is Leios, but how hard it can be to build it and to deploy it on Cardano, so that the whole community, and I think it's great that we have this opportunity to share that those questions and those ideas in such a venue, that the whole community really starts embracing this journey, and also be able to understand and potentially contribute, because I think that Leios will be a game changer, and there really is a need to start early how the whole community can contribute to ideas, suggestion, improvements, and so on and so forth. So great to be here, and thank you for the thread, Pi. It was a great way to explain Leios, and I learned stuff. It's great.
So you're at IOG basically translating science into engineering at this point.
Yeah, that really doing the bridge, and that's really something. I think that's something kind of. I think that's something also which is relatively new, in the sense, like as we're moving into the age of Voltaire, and there is really this idea that we want to help everyone understand how you go from this research, and everyone. Cardano is really renowned for being a research to have a very strong theoretical and research background, and very solid. But it's hard to see how you go from there to the actual thing you are running, and with which you're making transactions, and there is a I would say a transition to be between that needs to be taken care of, and a lot of questions that need to be answered before even you can start thinking of deploying something into even a testnet. So that's really the goal of this project.
Well, let's in the interest of time, why don't we dive into talking about what even is Leios? So I think the best format for this is I put together this this kind of short slideshow that explains basically my understanding of Leios, just from reading the paper and reading the kind of goals-oriented CIP that was put out a couple years ago, or maybe I don't know how long ago. Time is an illusion these days, but and then I'll kind of just go through my explanation of it, and maybe Arnaud, you can hop in if you have corrections or like extra flavor that you want to add, and Rick, you can jump in, or Denicio, if you have questions, if there's anything that I say that you want kind of me to drill deeper on. Does that all sound good to everyone?
Perfect.
Cool. So I think a really important thing to start with, understanding Leios, is the distinction between bandwidth and latency. And so this will also introduce the visual language that I'm using for kind of the rest of these slides. Cardano is a network of servers or nodes talking to each other, meaning they've kind of established a connection to each other. And so I'll represent those nodes throughout this as these blue circles with white arrows between them. And when they send messages back and forth, those messages have to propagate over this wire. And there are two there's more than two, but the two really important properties to understand when it comes to Leios. One is bandwidth, and that is how much data can you transmit per kind of unit of time over that wire. So in this example, you can see, on the left, there's a small circle, which means a small amount of data. And on the right, there's a big circle, which means a big amount of data. But you notice that data arrives at the node at the same time. Similarly, there's another kind of dimension you can look at, which is what is the latency? What is the time it takes to send that data? And so here, these both have the same bandwidth, but you'll notice that the message on the bottom gets to the node much faster, and it can even, in that time, send a return message. And so, the whole picture is you can combine these things in multiple different ways. Obviously, the ideal setup is a high bandwidth, low latency connection, but it's just kind of wanted to drive home that these are two different questions, and the two research extensions that you talked about for Ouroboros are really how do we increase the bandwidth of our protocol, and that's Leios, and how do we decrease the latency of our protocol, and that's Paris. And so the next kind of concept that's important to understand for Ouroboros Leios is this notion of Cardano forms a gossip network, which means that of the 3,000 plus stake pool operators and who knows how many other full nodes, they're all going to form this mesh where some nodes are connected to some other nodes, not necessarily every other node, because that would be infeasible. And if I want to send a message from this node here at the top to this node here at the bottom, I need to have multiple hops along the way. And if we want to send a node to everyone, or a message to everyone, and we want to broadcast it, we can't just send the message directly to everyone. And so an efficient way to propagate that message is, we call it gossiping, which means that this node, when it has a message it wants to transmit, will send it to its neighbors, which will then be received by these two nodes. And then they, in turn, will gossip that message to other people. And importantly, the rate at which these messages propagate is dependent on both the bandwidth and latency of these connections. So if you remember from my other slide, basically we call this the diameter of the network of, if you pick, what is the longest time that it would take a given size packet of a given sized message to propagate across the network. All right, so I'll pause there. Any questions or clarifications before I kind of dive into the next step?
I just wanted to add there that actually, in the context of Leios, we are talking more about the throughput versus the bandwidth, because the bandwidth usually is the capacity you have, and the throughput is how much of this capacity you can.
Sure, that makes sense.
Yeah, so that's and just to iterate, actually this whole I don't know if that's everybody's aware of that, but this latency, the time it takes for one packet to go through across the network, is probably one of the most important parameters of the network, and one of the most important data and value we talk about. And this is a thing called the Greek capital delta that people might have come across, and it's a very important characteristic of the network. So.
Yeah, and I guess that distinction between bandwidth and throughput, basically the whole point of Leios is to get our throughput as close to our bandwidth.
Yes, exactly. And we might come to it a bit later, where, I mean, if when we go into the detail of maybe the capacity, or what we can expect from Leios, but I think there is technically in the paper the throughput is expressed as a relation with the bandwidth, the capacity you have, and you can actually fine tune that. So that's an interesting also thing that we can explore.
Yeah. All right. So next, I'm going to talk a little bit about how Cardano works, and this is kind of a simplified model, as is everything that I talk about, because the details can get pretty subtle and nuanced. But I'm really just trying to, again, give people that intuition for what's going on. So on the Cardano network, every node has its own personal view of what the history of the blockchain is. And sometimes that, I'll call out here that view doesn't always agree, right? So this node here at the bottom, it is kind of currently preferring this chain ABX instead of ABC. It may know about ABC, but for whatever reason, it feels like X is a more likely extension for the network. And that's usually based on like stake and things like that. Not really important here. But basically constantly, the nodes are going to be gossiping the pending transactions in their mempool. So if a transaction comes in, somebody submits a transaction through Blockfrost. Let's imagine this node at the top is one of those big beefy Blockfrost nodes. It's then going to propagate that message to other nodes, and they're all then going to have those transactions in their mempool. It's important to note, in this example, every node ends up with the transaction, but sometimes that isn't always true because there's like a broken connection between two nodes, or it doesn't have enough time to propagate across the network. But in general, these transactions are just constantly being gossiped and propagated around the network. But they're just pending transactions. Nobody's committed to kind of including them forever. And if nothing else happens, they're just going to be thrown away after a short period of time. And then every second, every node is rolling a dice, and every 20 seconds on average, somebody wins that dice roll, which I've expressed by rolling a 6 here. I probably should have used D20s, but that's okay. And that node, the person who wins that dice roll, which there might be multiple in any given second, that's called a hype battle, but is going to then create a new block. And they're going to do so by taking all of the transactions they know about in their mempool and including them in the actual bytes of the block. So here, D includes these 3 transactions. And note the red transaction, like I was talking about before, nobody else knows about yet. But then that node is going to propagate that block to its neighbors. So it's going to gossip about it. And as those nodes receive that block, they're going to extend their local view of the world and remove any transactions that were included in that block or that are invalid now from their mempool. And in particular, note this propagation is what transmitted this red transaction. And that'll be important for kind of why a naive approach to scaling Cardano doesn't work later. And then these will gossip it to their neighbors. And then notice down here, this node received this D block, removed the transactions it knew about, but there's still transactions that can be included in other blocks. And then finally, every node is going to go through a process where they kind of update their view of the longest chain. So this node at the bottom here says, oh, well, C is getting extended instead of X, so I'm just going to switch to that view of the chain. So there's a lot of detail I'm kind of brushing over here, but just to give you an intuitive understanding, this is what we mean when we talk about propagation times and propagation delay. And Marcus, I think, has lots of really good numbers on this, but I think on average, the network performs this whole process in under a second. And so it's a pretty efficient network. Sometimes it'll take a little bit longer, like up to 3 or 4 or 5 seconds. But we want this to be really fast. And I'll explain why that is in a little bit, or I guess right now. So the problem, or before I move on, anybody have questions, or Arnaud, you want to add any kind of clarifications there?
Yeah, I don't have any questions yet. This is
clear until now.
Perfect. Thank you,
Cool.
Professor Pi.
So why then do we not just publish bigger blocks that can include more transactions? Or why do we not just reduce the time between blocks? So we're producing a block every second. If we're propagating these blocks, across the network on average, or in most cases in less than a second, then, why not just do that every second? And the main problem is that creates a world where every node is way more uncertain about what the longest chain is, right? So they're going to have all of these different forks, and it can be very difficult for the nodes to reach agreement on which fork to extend, because the next time somebody comes to produce a block, it's going to be difficult, or they may choose one that the rest of the network hasn't kind of settled on. Because, for example, if this node, the one on the left here with ABCDZ, if they choose to extend Z, then there's two other nodes on the network that haven't even seen Z, and so they won't be able to. They'll like basically think you're talking gibberish. They're waiting for the Z block to get to them. And so if you do this too frequently, or conversely, if you do this with blocks that are too big, the network isn't actually going to reach consensus, and you can have like long-lived forks, and you can have, I think there's even attacks where a malicious actor can start to bias the randomness of who gets selected to elect leaders, which means they can ratchet up their control over the number of blocks that are produced. So it basically is very bad if we were just kind of to take a naive approach. So what if we were to propagate smaller blocks? So for example, we already sent the transactions around. So if I go back to this slide, right, in theory, by the time that a block gets produced, most of the nodes on the network are going to already have seen this transaction because we gossiped it around. And then when we produce a block, we're retransmitting the same data because it includes these transactions.
Yeah.
So why not just say, oh, well, and where is it? Why not just say, oh, the blocks that we're going to propagate are just the transaction IDs. And we say, here are the transactions that we're committing to. Look at your local mempool, or look at the transactions that you've seen, and those are the ones to include. No reason to send them again. But the problem is, notice these blocks here have a reference. I use the little arrows for like reference by transaction hash. It has a reference to a transaction that this node hasn't seen. So, what if that transaction is completely made up? How can the node commit to and reach consensus on including that transaction if it hasn't seen it? And this would be fine in theory if we could rely on eventually receiving that transaction, and we could rely on that transaction being valid. So we could just wait until that transaction is propagated and then commit to the block, and things would work out great. The problem is somebody could include a transaction that doesn't exist anywhere, that nobody is going to be able to propagate. And this can create, like I said, a lot of uncertainty in which blocks to finalize. It can create long-lived forks. It can kind of denial of service the network. It's very bad. And so the solution that Leios proposes is we do this. We say, okay, we're going to pre-commit to transactions we may not have seen yet, but only if we see a certificate or an endorsement that that transaction exists and is valid. So here I've put the little plus here because now the nodes have seen a signature, or, and we'll talk about the exact scheme in a little bit, but they've seen some endorsement from a majority of the stake. And we're assuming in all kind of blockchain protocols that a majority of the stake is honest. They've basically promised, yeah, I have that block. If you need it, come to me and you can download it. And I've checked it for validity. And so with that, we can kind of breathe a sigh of relief. We can say, even though I haven't seen this transaction yet, I can accept this block. And this isn't exactly how Leios works, because doing exactly that at scale has a bunch of problems that I think the paper goes into, but it essentially just doesn't work out exactly. And so, there's some weird thing with my slides here, but and so the way that it actually does that is we break the protocol up into multiple different types of blocks. The first one is an input block, which basically takes the place of that mempool transaction propagation. So now somebody like the BlockFrost node that is receiving lots of input transactions just makes an input block of a bunch of transactions, and they propagate and gossip those around the network. And then other parties will say, hey, I am endorsing these transactions. So I have downloaded these transactions and I've verified that they're valid. And they include those by transaction ID into an endorsement block and propagate that around the network. And Arnaud can maybe provide some flavor on why this is the case, but they can also include other endorsement blocks. So it creates this kind of tiered validation. And then once we've accumulated a majority of the stake, right? So these endorsement blocks are basically votes that these transactions are available and valid. Once we've achieved a majority of the stake, we include those in a slow, high consensus Ouroboros Genesis style ledger to commit to them in a specific order. So we could go a lot more in depth on all of that. This is kind of the intuitionistic view, just so that we can, the rest of this conversation makes sense to people. Any questions or things that you want to add, Arnaud?
No, I think you kind of provided a good overview. I mean, given the time frame we have, I think the protocol is pretty complicated. I mean, it's like more than 23 pages of dense mathematical notation and 0.8 text. So there are a lot of stuff to unpack here. But I think you really gave the nutshell. Just on the endorsement process, I think you mentioned it, but there is really this idea in the various stages of the protocol. The way it's currently designed and it's defined in the paper, there are actually two stages of voting, which are important because the first stage of voting actually define allow an endorser block to group input blocks. So you have the first stage where you have all those transactions and data accumulated in a single endorser block and endorsed by a majority of the network. But then, in order to avoid certain kind of attacks, because a malicious actor could potentially only produce endorser blocks which contain malicious input blocks, or only, malicious being a wide, a vague term, but in general, something that is interesting for these malicious actors. So there is a second stage voting where you actually, in order to cope with the rate at which the input blocks are produced, you need a second stage of voting, and the second stage of voting is where you produce and vote for endorser blocks, which point to endorser blocks. So you have the typical, computer algorithm things where you kind of benefit from a tree of things to end up with a single root where you just have a small amount of data, but which is pointing at a full tree, and that's this final endorser block which gets potentially included in the chain by the classical Ouroboros Proust consensus.
Yeah, and I do have a question at this point. So you have Pi demonstrated earlier the current model of Cardano and how it works, and then here on the screen we have the Leios model with the input blocks, endorsement, and ranking blocks. Now, those appear to be more complex, but in what ways is this more efficient than the current model? Or is that what you're getting to next?
Well, so that's the end of my presentation, and we can kind of just converse about it. The way that this is more efficient is that we can basically always be transmitting input blocks. So, if we talked a bit about like bandwidth and latency before, but our bandwidth, we're basically using 1/20th of our bandwidth because we're waiting 20 seconds in between these big blocks that we're transmitting around once they get minted. And so by kind of structuring this, we can always be producing input blocks and very regularly be producing endorsement blocks, and then, relatively rarely, like once every 20 seconds, produce ranking blocks. And so because of that, like every message has a higher probability to include unique data, which means that we have more throughput on the chain overall.
Okay, thank you.
And I think that's
and so I was
Go
watching
ahead.
Professor Kia's video, and in my mind, my imagination was he had that bandwidth, right? And there was another presentation as well. So what I imagined in my mind was you're at a train station, and there's a bunch of different entry points, and everybody's standing waiting for the train. So you have this queue of people, and those are like the transactions for the input block, right? And then when an empty train shows up, each queue is your endorsement block. Each person is a transaction. This train shows up. Hey, that's the next block. Everyone's already queued up, and everyone just files right into the train, not all at one time singular, but all these parallel lines, they're all filing in to fill that block up, and off the train goes very quickly, and you're not waiting around for people to get on the train. That was just kind of my imagination of how you're filling this block up more rapidly with organized transactions. Is that a good analogy, or am I kind of off track here?
Yeah, it's more like, to kind of take your analogy, today on Cardano, when you get on the bus, everybody's bringing their backpack and their suitcase and their luggage. And so you can fit fewer people on the bus. But now with Leios, everybody ships their suitcase ahead of time. And they kind of send that to their destination. And then they can just get on the bus, and it's just them. And so it's more like planes, right? Where planes, you put it in the underhold, and then you can fit more people in the cabin of the plane. It's kind of hard to kind of adapt.
Yeah, the analogy is hard to
fly, but the basic idea of like a bus can only leave so frequently, and so the more we can do to fit more people into that bus, the better. And the way that you do that is by you make the individual things that you fit on the bus smaller. So you go from a person with their luggage down to just the person, right? And so that's going from the transaction, which you've already shipped off, down to just the transaction hash, where you can okay, it's actually important to include the person on the bus. You don't want to just ship luggage around, but you can kind of do that much more in bulk.
Okay.
And the endorsement, the stage of endorsement. So the whole idea behind, so Leios is also known as input endorsers. There is this term was floating around, and the whole idea behind endorsers is that you are delegating, or you as a node are delegating the validation process and the packing to other nodes, and that's the voting process. Which means that basically once you have an endorsement block, you can be sure that this has been vouched for by a majority of the voters, and that's what the certificate is about. And if you do that at the whole level, then at the end, what you get is an endorser block, which contains references to references of references, and that you can just say, oh yeah, is this valid? I can verify certificate, and then I can include that. So you have much less work to do. And I think that's one important characteristic of Leios, and the way we can achieve this speed is also the fact that Leios is a trade-off between the maximizing the throughput. So saying that we have this capacity. So every machine on the internet right now, and every node and block producer basically has 10 of megabytes of bandwidth available, right? Right now we are streaming videos, and this consumes a significant amount of bandwidth. So machines and the network generally have a lot of bandwidth available, which is not that much used in Cardano. And Leios is just saying, okay, let's use more of that bandwidth. So let's increase the throughput, use more of that bandwidth. But to be able to do that, It's just like you need to pack more things together, and then this means that you will make more time. You need more time to make sure that all those things have been validated and go through a process. So basically, I've tried to convey this analogy by making the distinction between a big ship container where you can pack thousands of containers together, and a smaller ship where you just put one article or your bags and packs. So by packing things more together and giving it the time to reach the destination and to go through the whole process, then you actually increase the throughput. And even more importantly, what's interesting with the way Leios also is designed, that if you do this naively, like a single stage, you will end up with a lot of latency lost, because then it will take a lot of time to pack those big containers through the whole process. But what does Leios is that it says that the node will do that in parallel. So you will run all those stages through several pipelines in parallel, which means that there is always some part of the system and some part of the node which is in one of the various stages, which means that you have all those parallel pipelines, each processing transactions or voting or creating endorser blocks or accepting endorser blocks. And because it's done in parallel, you really maximize the whole throughput of the system.
Yeah, so less waiting around. There's a good follow-up question in the chat, Denisio. I don't know if you want to bring that up from Matthew Feisenberg. Are we going to see specialized pools regarding each type of block? Thank you, Matthew Feisenberg.
So I think this is a good chance to kind of highlight that difference between science and engineering, right? The paper really talks about the fundamentals of how do computers work and what is the safety properties of this. But there's lots of engineering details like this one that still need to be kind of hammered out and decided on. So you could, for example, see specialized pools for each type of block, and each stake pool operator decides, 1, 2, or 3, which subset of them they want to run. Or it could be just the same node software, and your same stake pool operator keys are going to roll these dice, and perform all 3 rolls. It remains to be seen what the best model is. What is really interesting, though, is that because we are rolling more dice, this is an opportunity to design a more normalized reward scheme, right? One of the big challenges for small stake pool operators today is that, really there's only so many blocks that get produced in an epoch. And so small stake pool operators, unless you have 2 or 3 million ADA, you're not going to produce a block for many epochs at a time. And so even though you may have almost enough ADA to produce a block, you get 0 rewards. It's not like it scales down and says, okay, you're going to get part of a block reward. By having more blocks that are produced more frequently, that are kind of less resource intensive as well, you can have smaller stake pool operators have a more normalized rewards where, we always say in expectation, everybody's receiving the same thing, but for small stake pool operators, that often isn't true because they go so many epochs without receiving any rewards. And so this kind of really flattens out and smooths out that curve. And so it's a really exciting aspect of the Leios model.
Are you, Pi, are you saying basically that the smaller stake pool operators with lesser stake, so that's lesser than 3 million stake, would also be eligible or elected as what the...
Yeah, and I mean, a huge caveat that we've got to figure that all out, right? Like, it's still got to be built and designed. The Leios paper doesn't say how the incentive model for Leios should work, or I missed that section if it does. But what it means is that, like, input blocks are something that are produced, for example, 5 times per second, right? Or even more frequently. And so because you're rolling more dice, you just by nature have a higher probability to produce an input block. And so if there is some small monetary reward attached to that, then that means that, as a small stake pool operator with 500,000 ADA stake, you're more likely to at least get some rewards, right? That difference between 0 and some is much bigger than some and some plus 1. And similarly with endorsement blocks and all that. So
I think to maybe to add something about answering directly the question, Mathieu's question, I think one important point to keep in mind is that the security of this whole thing is predicated on the fact that you are voting and producing certificate, which is based on stake. Which mean that to have a valid endorser block, or to have a valid input block, or to have a valid layout ranking block, whatever, you need the majority of the stake to agree that this is indeed the block, and therefore it's hard to imagine. Maybe that could happen, and as Pi says, our R&D work will also include. I mean, we'll also need to explore the questions around how practically we are going to implement that. But there is a whole question that, well, to be able to vote, you need to have stake. So if at each stage you need to have stake, and if you start thinking like, okay, you are going to distribute stake in different kind of things or different type of rule, it becomes a bit complicated to understand, and the security of the whole network becomes, complicated to really qualify. So really what's inside the paper is just to say, at each stage you will have a stake-based voting scheme, and this means that, well, all the nodes and all the stakeholders will have to participate in these things, because otherwise you are basically giving more room to adversaries to say, oh yeah, if I need less stake to be able to mint or to create an endorsement block, I will do it. Right? So there is this. So it's not clear to me. I mean, you really need to think about the fact that what's different with Leios. Leios sits on top of FRAUs. So you still have FRAUs. You still have all the thing about the stake distribution. You still have all the thing about producing blocks on average every 20 seconds or whatever the slot frequency or the block frequency is. So you have FRAUs, and you are layering Leios on top, and what Leios provides is a set of schemes and techniques and algorithms to increase the amount of data you can actually chain indirectly in the chain. But Leios rests on FRAU, so you will still need to have those stake pools and the stake distribution. And actually, the stake distribution at each stage of the process is a parameter that needs to be taken into account by Leios itself to process data. So that's important to know. And
so,
go ahead.
Sorry. Yeah. So I think also I want to ask kind of from the user experience as well. What is Leios? Because that's important. And Pi is really good about user experience. He really gets that well, with Sunday Swap and stuff like that. I use that, and it's fantastic. And so if you have Leios running and there's higher throughput, but there's still some notion of a maximum block size, what kind of an improvement from the user experience would you see? For example, right now, the network is under very modest load. It's 20 to 30% roughly. And when I interact with the DApp, it's pretty quick. The user experience is pretty smooth, but we all know that when the network load gets up into the 85 to 90% range, 90, 95% range, it's giving the user a whole lot of back pressure. And there were on rare occasions I was fighting to get a transaction in. How does Leios kind of get past that back pressure, or in other words, support a better user experience? So when you get that kind of back pressure from the network, like what kind of improvements would we expect to see?
Yeah. So the reason that experience is coming up, to kind of connect it back to how Cardano works, is because each of these nodes, right, when I put these transactions on the side here, each node has a certain capacity, right? It won't just fill up with transactions forever. It says, oh, I can fit at most 3 transactions, for example. I mean, it's many more. It's twice the block size by default, and every node can configure their own capacity. But what ends up happening is, as this propagates, maybe these 2 nodes at the bottom are already full, and so these transactions won't propagate to these nodes at the bottom. And so if those nodes at the bottom are the ones that are selected to produce the block, well, it won't include your transaction. The plus size is it will clear out their mempool, and so now your transaction can propagate to them. But the reason that when the network is under load, you see longer confirmation times for blocks is either because the node you're submitting to is full, in which case your transaction will get rejected entirely, or it's taking longer for your transaction to propagate and find the node that is going to produce the next block. And it may miss that bus, right? It's running late because it's having to push through the crowds, and so the bus leaves without it. From the user's perspective with Leios, because we are propagating these transactions more continuously, you may still see it takes, how do I say this? So there is always going to be some load limit where the network has to start pushing back on the load, right? There's just no such thing as an infinite data processor in our finite universe. But what this does is it raises that ceiling quite a bit, because the blocks that are getting produced every 20 seconds can include more data, right? And so, yeah.
Maybe to continue on the analogy of bus is the fact that with Browse, you have one bus leaving the network somewhere in the 3,000 plus stake pool every 20 seconds. With Leios, you have, if we say, for example, we have 1 input block every second, this means that you have one bus leaving every second. So that's 20 more buses.
Perfect.
It means that there is a lot. But wait.
If you miss the first one, you get the next, basically.
Yeah, and potentially in the network, depending on how your transaction travels across mempools, chances are that maybe you sit in a mempool of a block that doesn't produce an input block now, because and the transaction cannot be propagated because the other blocks appears are full. But then the next slots or the next time this block gets lucky and produces an input block. So you have much more chances. I mean, you spread the load of producing input blocks across the whole network, and this comes at a price, and the price is latency. The price means that now you have your transaction will be included in the bus, but the bus will take more time to travel because now it will have to stop through the first Mendoza block and then the second Mendoza block, and then it will be included in the chain, right? So there is this kind of offloading process or repackaging process that happens, which needs to happen for the block to be included. And the underlying block production for Browse will stay untouched. It's still like a clockwork, 1 every 20 seconds on average. But now you will have your transaction potentially included among many others, and much more than what is currently the case for Browse.
To kind of put a finer point on that as well, like that latency is essentially when you can consider it final, right? So that's the finality. And there's some interesting, I see Matthias has some great questions about how this all interplays with Paris that we may not get the time to talk to. I don't know how long we can go on this, but
we have a couple minutes left. That's okay.
There's that finality question of when can I breathe a sigh of relief and know that my transaction is going to be included in the ledger for sure? But the kind of converse there is, because it's getting included in input blocks and endorsement blocks, you can start to build that confidence sooner. And it's not a for sure gung-ho, even in getting included in a block is not for sure gung-ho, but you can start chaining transactions on it easier because you don't have to worry about, hey, is this chained transaction that I'm building on top of it going to sit in the mempool as well and maybe have a higher probability to get invalidated. Because transactions are getting included in input blocks and endorsement blocks, they're building that confidence that that nodes have checked and validated those transactions before it even makes it into the ranking block. I think that's true. I may be misunderstanding that, but
Gentlemen, there's a couple of more questions coming in. One of them is from Thomas, and Thomas asked here, do blocks contain only transaction IDs? And his second question is, are full transactions stored separately, finally, on every node?
I think this is, again, a question that requires us to do the engineering, right? That's the way I picture it, of like, oh, a block is committing to a set of transaction IDs for an endorsement block, and an endorsement block has a set of transaction IDs for input blocks. And then the input blocks actually contain the contents of the transactions. And so at the end of the day, yes, every node has to store every transaction, right? Because if somebody's replaying from Genesis, they have to be able to download that transaction to know what ledger state changed. So I think there's some really interesting research down the road as well for pruning and being able to do that safely and things like that. But in essence, yeah, every node has to store every transaction for now with Ouroboros Leios as it is. Yeah.
Maybe I can add something here, which is I think this is something, and this is something a bit new to me also, is the fact that we think of the input blocks in Leios as containing transactions. But what if they contain something else? Data, transient application data. I think a very good use case, for example, is voting. If you when you have a voting round, and if you vote at the scale of, for example, the scale of Cardano, or you have like potentially tens or hundreds of thousands of voters which can be involved, and is it really interesting to keep all those votes around forever if you have a cryptographic proof that actually the result was actually correctly computed from the vote? And Leios could potentially be also used to ship data around and make that data part of the blockchain, but without it being transaction. And that's also something that we kind of discussed just yesterday with Yorgos, who is one of the researchers, and this kind of blew my mind. Say, oh wait, this is like what you're saying, like you can have like arbitrary data being kind of
it's like an ephemerality dimension of saying,
yes.
Hey, we want to propagate this in the same way that we would propagate a transaction, but we only need it for this window of time. And it kind of builds a data availability layer into Cardano, which is really interesting.
Yeah, exactly. And that's also something I think that we talked to. I mean, we kind of gloss over the questions by saying often there is engineering work to do and R&D work, and I think that this is exactly the kind of thing we really want to do during that R&D and engineering and I would say maturation phase and process, and also the kind of thing we really wish the community can help us on and can chime in, saying, hey, yeah, we have potential use cases where actually this massive increase in throughput would be very useful. Maybe not for transactions, because if we start thinking of shipping all those transactions and increasing like I don't know X times the number of transactions we ship around, well, this means that we have to store them and we have to validate them every single time, and that's going to be quite expensive too. So that's also something interesting to think about.
One question to that. There, because you mentioned earlier, Pi, that certain stateful operators would be able to choose which type of blocks they would like to produce.
Maybe. We don't necessarily know how it all is going to work, but that's like one option we could explore in the engineering effort.
Okay.
Yeah. No. Oh, sorry. Go ahead. I was going to say something I see that's very helpful here is if you look at the nodes currently, how much CPU consumption there is and the bandwidth. The bandwidth is pretty low on the Cardano network.
Yeah.
Like the consumed network is very, very low. It's very, very efficient. And the CPU consumption, it sits very low for long periods of time, then it'll jump and then come back down. And so it sounds like you're going to just fill that up so it's much more efficient and you're making use of that processing. Sorry, Denisio, is that where you're going with that? I didn't mean to, but is that the case?
Partly, actually, but for me, it was more from a stake pool operator as a perspective. What would really change? Because it sounds like there's a lot of changes can be expected with Leios. And I'm expecting with these changes and introduction, of course, of the new block types, that things will change, really. So
that's really something, again, this is something that we need to figure out exactly. We know that Leios will change things. We know that Leios will be really change the way the network operates and the way the node operates. The question is how. And one of the things that we didn't talk a lot about it, and probably it's not the right venue. And people might be. If people are interested, they can always chime in. We have channels, and we are doing this is open, so I can ask more questions. But part of the engineering work and R&D work we are doing is really focused on the question of resources. So really relating. So we have a bright new shiny algorithm, right? Which is great, and everyone is excited about it, and people are thinking, yeah, we are going to have like X throughput increase and that many transactions and whatever. Okay, great, but what's the cost? What are the impact in the resources? What does it mean in terms? Exactly the question you're saying, Denisio. What does it mean for stake pool operators? If you can't run anymore your stake pool on a Raspberry Pi, maybe that's not great, right? Because it means like the requirements for a stake pool might be much higher, and it's not great for ultimately it's not great for security, because it means like centralization. If you need more resources and those resources cost more, this means like you might push for you might change the topology and the structure of network. And so these questions, we don't have the answer. This is really just just the beginning. But we need to answer those questions, because those questions are critically important also for adoption and also for deployment. There is also this something which is kind of dear to my heart. Like, as an engineer, as a software engineer, there is nothing I hate more than big bang deployments, because big bang deployments make you super shaky, and if something goes wrong, then the whole world stops. And that's that's terrible, and that's something you want to avoid, because I don't want to be woken up at 2 a.m. in the morning because something went wrong. So we will also, I think we also need to figure out, okay, is there an adoption path for Leios? Are there intermediate steps between now, where we have a paper, and the future, where Leios is humming and buzzing in every single node across the planet? Maybe there is an incremental path where we can say, okay, we can build Leios for some use cases, some part of the system, and test it, and maybe identify like interesting points to work on, identify integrations points, identify how to best put that within the existing structure of the node, within the existing infrastructure of Cardano. So these are very exciting questions also, which are very practical in terms of the software, and the paper, the research doesn't answer those questions, of course.
Yeah. Let's fast forward the slides all the way to the last slide, where this is the current how it works, and we want to have those slides on Leios and how does Leios work. This is what we're talking about here. So anyone who just joined, I see we got 4,804 viewers on X, and there's at least 16 viewers here right now on YouTube. So thanks to all the viewers and the questions. And we had some questions from Matthias as well, Matthias Bencourt. And so let's hit that before.
K-Tor-Z on Twitter, for those who don't know.
I don't know who is this guy. I can take this one. So there is definitely an overlap between Peras and Leios, but it's rather on the positive side. Is the fact that both Peras and Leios strongly relies on voting, which means that we are currently exploring voting for PRAS. So I mean, I could talk about it more, but that's not the point in the discussion. So we are really trying to figure out what would be the good voting scheme and the right way to build certificates for PRAS. I think that among the many Twitter thread that Pi is doing, there was one recently about Albaz, which is a new technology for building certificates, which we are really considering seriously for this kind of certificates. And the good thing is probably that if we figure out voting for PRAS, we'll figure out voting for Leios. When it comes to bandwidth and resource consumption, that's also something we need to figure out. But the hypothesis is that voting consumes a fraction of the bandwidth that input blocks would consume. So even if you and remember that things happen in rounds, so you don't vote every second. You vote potentially every 5 or 10 seconds, depending on the length of the windows you are considering. Which means that you have potentially, several seconds to ship around the network, maybe a few hundreds or a couple of thousands of votes, which are very small. So that's not much data ultimately. So there won't be that much competition at the bandwidth. There might be timing issues regarding how long would it take for those votes to reach network. And one of the things we really also want to work on is to refine our simulations analysis to take into account the effect of more bandwidth dedicated to input blocks to voting propagation, because this could have an adversarial effect, especially if you start seeing variations in the bandwidth, or you are cut off half of your nodes or half of your peers, and or you have a surge of peers connecting to you. So now you have your bandwidth has to be shared across more nodes. So there is a whole interplay here which needs to be explored. But at the end of the day, I would probably don't think that's impactful on the bandwidth side of things.
Thank you. Thank you there, Arnaud. Matthias did have a follow-up question to that, I believe. Do we anticipate that we can somewhat merge Paris and Leios and reuse endorsement for Leios as Paris acknowledgement? Who wants to take that?
I can't take that one.
I think it's really only something that the researchers can answer. It makes sense that, if somebody is committing to, hey, this transaction is valid and available, that commitment, that kind of endorsement and voting could be double counted for both the kind of Leios data availability propagation sense and the, hey, I'm going to prefer blocks that include this fork, or I'm going to include forks that include this block. I'm going to give them preference. It seems like they should be kind of similar, but I'm sure there's a ton of subtlety that I don't know if the researchers have directly considered, or at least not published anything about that.
Hopefully that answers your question, Matthias. Thanks, by the way, for participating. We also have another question, just in time. I'm trying to be conscious also of time. We have one more question here from Tiago. Who holds the input blocks, and will they be propagated through the network? Second question. And the third, I guess, is how was the disk space problem resolved?
I'm going to kind of point back to this being largely on the engineering side and less on the science side. In principle, the paper assumes that, yes, the input blocks are propagated through the whole network. That's how the people producing endorsement blocks can know about them to include them in the endorsement blocks. And it kind of, in my mind, and this, again, is more engineering than science, takes the place of the current mempool propagation, where instead of propagating individual transactions, we just let blocks propagate these input blocks so that we're not retransmitting data. I don't know if that's actually how the researchers envisioned it, if they also envisioned a phase of mempool propagation before that or not. But yeah. And I don't think Leios addresses the disk space problem specifically, right? If you have higher throughput and you are storing that data, you're going to have a higher disk space requirement. I do think that is probably an avenue for other research by other entities for another extension of how can we safely truncate history, for example, or compress history down into zero knowledge proofs where you can get it from an archival node if you really need to, but for the most part, running day-to-day nodes don't need that history, for example. But it's not a question that's directly addressed by Leios itself. Since we're coming up on time, I do want to kind of make sure we close on a particular note around, we've talked a lot about the theory and engineering and how it works, but we haven't talked a lot about but what is the throughput we can expect? And that, on my part at least, that's been very intentional because, I've seen a lot of numbers thrown around on Twitter, and the simple fact of the matter is we don't know what the throughput of Leios is until we do more simulation and benchmarking. I think it would be a mistake to go out there and try to kind of strongly claim that it's going to do XYZ transactions per second. Partly because, as has been addressed in many other places, transaction per second is kind of a very it is a difficult to normalize metric, meaning it is difficult to hold many different blockchains to the same standard of what a transaction is, right? In this, does an endorsement block count as a transaction if it's a message being passed back and forth? So it's a really complicated thing to say, oh yeah, this is how you should define transactions per second, and thus here's what our throughput is. But also because real world factors come in a lot, right? What Leios shows is that we can much more efficiently use the resources that we have, and we can kind of get asymptotically close to optimal use. But the constant factors in any asymptotic analysis, as Aiken is a brilliant example of this. The asymptotic factors in the real world make all the difference in the world. So I think we need to do a lot more benchmarking, and I think it would give us kind of that very short-term endorphin rush to say 450,000 transactions per second is one of the numbers I saw somebody throw out there without any I could not find where they got that number, right? So it's just an arbitrary number. So we shouldn't take that short-term hype win and lean into any particular TPS metric. What I think we should do is just do the engineering and the R&D to make it a reality. We know it is going to be a significant improvement just because of the fundamental inefficiencies in the current network and how much time nodes are waiting, but we don't know any specific numbers, and I think it would be a mistake to try to push any specific numbers. I think we as a community have made that mistake before, and so I've been kind of cautioning people to be cautiously optimistic about what this is going to provide, but let's declare victory once we've actually built it.
Exactly, and of course the benchmarks has also been done, benchmarking.
I think there's been a little bit of benchmarking that was done early on in the project, but I don't know of any comprehensive benchmarking on now that we have the kind of final Leios research paper that kind of takes all that into account.
Yeah, there was benchmarking on Hydra, but I did not see anything about benchmarking on Leios. It would probably all be theoretically because you got to write the code first. But I got to tell you, Pi, I love this podcast. You're the best teacher I know. You really are. I totally enjoy every time I get to hear you speak. Absolutely love it.
Rick, before we close, Pi, I'd like to have just kind of how would you describe Leios, in 2-3 sentences? Sure. What is Leios?
Leios, I don't know. You kind of put me on the spot here. I'll let me find a meme that I posted that explains Leios very, very simply.
Okay.
Here. I'm going to share screen. So this is how I would summarize Leios.
Okay, that does it for me.
Beautiful.
I'll take that.
All right. Pi, thank you so much. Again, this roundtable series is Roundtable Talk series really proves, it proves its value. I mean, through education. And I think this is really, let's say, it enhances really the community understanding of really complex matters. And of course, Pi, I really would like to thank you. I know Arnaud had to leave a bit earlier.
That's okay.
Thank you as well, Rick, for co-hosting today. You've been wonderful, really, absolutely great. The questions were wonderful. Thank you, everyone, also for participating. Your questions, I'm sorry if we didn't get the chance to answer each and every one of your questions. But yeah, hopefully next time we'll have a little bit more time. But for now, thank you all and wish you a good evening.
Bye, everyone.